All right, let's start by recalling some facts from last time that we discussed. So we proved that if we have an analytic function on a domain and a typical curve in that domain, whose interior satisfies, so the interior is contained in the domain except for possibly finitely many points, W1 through WK. So I've illustrated the situation here in the picture on the right. So you got a curve gamma, and the interior of that curve, that's all in the domain except at those red points, the WI. And we showed last time that the integral around gamma is actually just the integral around those blue circle curves going around the points. So if you take suitably small radii for those circles around those points, all those circles, they won't intersect, so they'll be mutually disjoint. And in that situation, you can apply Green's theorem to the region in between the blue curves and the original curve gamma, and then so using Green's theorem, you find that the integral around gamma is equal to the sum of these integrals around the blue curves, the blue circle curves. So basically where we're going here is we're interested in what we can say about integrals around curves that enclose singular points of our analytic function, so points where the function is not analytic. And so this is our first step here, that we can take this integral here and we can localize it to these integrals around these small circles that just enclose a single one of the singularities. Right? And these blue circle curves, they can be as small as you want, as close to the W's as you would like. So in some sense, these integrals here are sort of localized to the singular points. So you take these, so any sort of arbitrary integral over a curve gamma can be localized like this. So it's a sum of these smaller localized integrals around the points. And essentially those localized integrals, they become up to a constant factor, what's called the residue. And that's a concept we defined last time. So the residue of a function at a singular point, z0, is 1 over 2 pi I times the integral around a small disk going around, the integral around a small circle, boundary of a disk going around that point z0. Okay, so that's the concept of residue. And then we see here just comparing this integral here and that sum to this. Well, we just have this factor of 1 over 2 pi I here that's different. So if we just insert the definition of residue into this previous equality up here, then what we get is this result down here, that the integral around that curve gamma is equal to 2 pi I times the sum of the residues at each of those singular points. Okay. So this is what's called the, sort of formally stated, the residue theorem is in this situation up here that the integral around a curve gamma is 2 pi I times the sum of the residues around those singular points. And the utility of the residue theorem is that it reduces our integration problem here to just a finite sum of these numbers, these localized numbers that are localized to the singular points. And it turns out that those numbers, those residues, are often computable by other methods, which are potentially less difficult than computing the integral directly, the integral that defines the residue directly. So one instance we worked out a little bit last time at the end was in the case where your singular point is a pole. So remember, a pole is where the norm of the function blows up to infinity as you approach that singular point. And what we worked out is that if that's the case, then you can always write your function as an analytic function divided by z minus z naught to the m for some positive integer m. In case you have an analytic function divided by this simple polynomial, and in that case, the residue of f at the pole is equal to this derivative, the m minus first derivative of that function k at z naught divided by m minus 1 factorial. And that was a simple application of Cauchy's formula for higher derivatives. If you just take this expression up here, right? So you're to do the residue, you're going to integrate f, but that's integrating this k over that power of z minus z naught, and you just go to Cauchy's formula for higher derivatives. That exactly tells you that that's this derivative of k times that constant factor, and also by so that's a useful formula for the residue, as we'll see. And we could also say that if by expanding k into a power series, this residue, you have this quantity here, that's the m minus first coefficient of the power series expansion of k. So when you divide that by the z minus z naught to the m, right, so that m minus first coefficient, that's what the m minus first power of z minus z naught, you divide that by z minus z naught to the m, and you get the coefficient of 1 over z minus z naught of f. So we can also say that the residue is the coefficient of 1 over z minus z naught in the what we call the Laurent expansion of f. And so f has this, when you have a pole, right, if you just write this expression out in terms of power series, you get what's called the Laurent expansion of f. And so the residue is just the coefficient of 1 over z minus z naught, so the negative 1 coefficient in the Laurent expansion. All right, so this kind of gives us two strategies for potentially computing the residue of a function at a pole. So the first one is that if you just offhand just kind of know the Laurent expansion, if it's easy to just write down the Laurent expansion of your function. So for example, maybe your function is the product of two familiar functions, and you can just easily sort of write down the product as the product of the power series, then it can be easy to extract the coefficient, the appropriate coefficient. So it might be easy to just do it directly. Otherwise, what you can do is use the other formula in terms of the derivative of that k. So you would try to write your function as this quotient of an analytic function and z minus z naught to the m. And then if you can do that, then that power of m there, you compute the m minus first derivative of that k, evaluate at z naught, and divide by m minus 1 factorial. That's also the residue. Okay, so we're going to put those two things into, we're going to put them to use, put them to work, and do some examples here. So first example. So let's look at residue of f at z naught, where f of z is z squared plus 3z minus 1 over z plus 2, and z naught is negative 2. Okay, negative 2 is clearly a pole here. Okay, because as you go to negative 2, this polynomial up top, just a polynomial, that stays perfectly nice and bounded, and then the z plus 2, that's going to 0, so dividing by that is going to go to infinity in norm. So that's definitely a pole. Okay, so there's two ways to compute this residue. So the first one is to realize that, well, by the second point up here, this f, our f is already, the numerator is a polynomial, so that's an analytic function, and the denominator is just z plus 2 to the first power, right? So that's our m, and so use 2 with m equals 1, right? And then you just have to take the 0th derivative of k. So this polynomial here, this is our k of z. And so you have to take the 0th derivative, right? Because you have 1 minus 1. I guess I'll write it all out at -2 divided by 1 minus 1 factorial. So you got 0 factorial, that's just 1. K, this k to the in parentheses 0, that's just saying 0 derivatives, right? So that's just actually just k itself evaluated at -2, and so that is 4 minus 6 minus 1, and that's -3. Okay, so this is equal to the residue of the function at z0. But it's also easy to use 1, so we can also use 1. And so in this case, we would want to expand things in powers of z plus 2, right? Z minus -2. And our denominator is already in that form. It's just z plus 2 already. And then we can take our numerator, so you can take z squared plus 3z minus 1. I guess I'll just carry around the denominator. And you can write this in terms of z plus 2 in the following way. Just a little trick. Z is z plus 2 minus 2, right? Then squared, so I'll put extra parentheses in there. Z is z plus 2 minus 2, and then minus 1 divided by z plus 2. And this is z plus 2 squared minus 4 times z plus 2, but then we have a 3 times z plus 2, right? So that's a minus z plus 2. And then we have collecting all the constants, a 4, a minus 6, and a minus 1. And notice that we already did that computation, that's minus 3, right? Because what we're going to see is, yes, we'll see that that's relevant in a second, because if we actually do this here, we can see this is -3 over z plus 2, right, plus, let me say, minus 1, and then plus z plus 2. And so there's the Laurent expansion around -2 of our function. And we indeed see that the coefficient of z minus z0 to the minus 1, that's this minus 3 here, right? So that, again, that's the residue of our function at -2. Okay. Right. And the next example will be another fairly easy one. We're going to look for the residue of g at the point 1, where g of z is equal to e to the z over z minus 1 cubed. And so in this one, or I'll say let's use the first method first. We'll just write down the power series expansion. So e to the z, right, that's going to have a power series expansion, a n z minus 1. We're expanding around 1, so we got to do z minus 1 to the n. And these a-n's, that's just equal to so we take e to the z, that's our function, the nth derivative of it. We evaluate that nth derivative at 1, and then we divide by n factorial. Remember, the nth derivative of e to the z is just e to the z, and then plug in 1, you just get e. So that's just e over n factorial. All right, so this is equal to sum n equals 0 to infinity of e over n factorial z minus 1 to the n. And so our g of z, equals, well, we just got to multiply this by 1 over z minus 1 cubed. So our first term, so let me just write this out explicitly. It'll be easier this way. So if we write this out, this is just e plus e times z minus 1 plus e over 2 times z minus 1 squared plus e over, and that 2 is a 2 factorial, 3 factorial, z minus 1 cubed plus etc. Right? And so g of z is just that multiplied by 1 over z minus 1 cubed. So we get e over z minus 1 cubed. We get e over z minus 1 squared. And we get e over 2 factorial over z minus 1. And we get e over 3 factorial plus dot dot dot. And just remember that the residue is the coefficient of the z minus z naught term, right? So this here, that's the residue. So e over 2 is the residue of our function g at 1. Okay. And then using 2, so alternate method, just to check our work, would be to, well, try to write our function as an analytic function divided by some power of z minus 1. But our function is already presented that way, right? So our g of z equals e to the z over z minus 1 cubed. This 3 is our m, and this e to the z, that's our k of z, right? So all we have to do to find the residue, so the residue of g at 1 is equal to the second derivative. So we have e to the z. We have to take the second derivative of that. We evaluate that at 1, which is our z naught, and then divide by the same 2 here, second derivative, 2 over 2 factorial. Right? And of course we're going to get the same thing that we got before. This is e over 2. And so you see that actually how much quicker the second method is. In both of these situations, the second method was much quicker. So usually the second, I found that second method is kind of the way to go, generally speaking. So let's look at a more involved example. So we'll find the residue of h at w for, let's see, where h of z is the principal branch of the logarithm divided by 1 plus z squared squared, and w is any pole of h. So to figure out the poles of this function, let's just make sure we understand the domain. So, I mean, the poles are points that aren't in the domain of your function. So it might help to just think about the domain in general. So the domain of h. Well, first of all, we have the principal branch of the log. So remember that we have to exclude the ray that goes from negative infinity to 0, including 0 along the real axis. And then we also have any point where this denominator doesn't, where the denominator gives 0. That's not going to be in the domain. So to see that, remember, so by the fundamental theorem of algebra, we have to be able to factor this quadratic polynomial. That has to have roots, and of course the roots are I and negative I, if we just think about it for a second. So what we can do is write our denominator there as z minus I So that corresponds to the root I, and z plus I corresponding to the root negative I, and then we have the square factor there. Okay, so we see also that we have to exclude the point I and the point negative I. Right. Okay. So none of these points in this ray that we excluded, they can't be poles, because poles are isolated singularities, and none of those points along that ray are isolated from the other points on the ray. So that can't work. So the only possible poles could be at the I and negative I, and that's pretty clearly the case. So to see that I is a pole, you just have to write your function as log of z over z plus I squared over z minus I squared. Because this numerator is an analytic function near I, right? Log of I makes sense. Log makes sense at I and near I, and z plus I makes sense at I and near I, and is not 0. So that numerator here, that makes sense, is analytic near I. So we have an analytic function divided by some power of z minus I. So that's the characteristic signature of a pole. And in fact, it's a pole of order 2, because log of I doesn't vanish. We'll come back to that. So then, on the other hand, for the other one, you could also write this as z minus I squared over z plus I squared. And that shows you that that minus I is a pole of our function. Because for the same reasons, log is defined at negative I, it's analytic near negative I, and z minus I is also analytic and not equal to 0, so that numerator is analytic near negative I. So the analytic function over z minus negative I squared, and that's the characteristic signature of a pole. So to see that these are poles of order 2, I know that's not, the question asked that, but you can note that log of I, that's ln absolute value of I plus I times the capital arg of I. And also that log of negative I is ln of the norm of negative I plus I times capital arg of negative I. And this is just 0 plus I times pi over 2. So this is pi over 2 times I. And this is 0. And that's ln of 1. 0 plus I times negative pi over 2. So this is negative pi over 2 I. So these aren't 0. Right? So if we look at this expression here, we have our h of z is k of z, where k doesn't vanish at I, divided by z minus I squared. So that says that I is a pole of order 2. So this implies that I is a pole of order 2. And this one implies, for the analogous reasons, that negative I is a pole of order 2. And that's for the function h, of course. All right. And then, well, it'd be very annoying to have to expand in this expression here and this expression here to expand that out in Laurent series. We'll just use the second method. So using 2. So for the pole I, our k of z is log of z over z plus I squared, and our m is equal to 1. Excuse me, I mean 2. I was getting confused because the formula involves m minus 1. So m is equal to 2. And then what that says is that the residue, so the main result of, so the method for point 2 is to compute the residue here at I by taking the m minus first derivative of k. So this is k prime evaluated at the z naught, so that's I, and then divided by m minus 1 factorial, that's just 1 factorial. So we just have to figure out the derivative at I, and that is not at all hard to do. You just have to use the quotient rule. So this is some computation here that I will allow you to do. I won't spoil the fun for you. And you get pi over 8 plus I over 4. Okay, so this is just a standard computation. And then for the pole at negative I, so for the pole negative I, our k of z was log z over z minus I squared. And again, our m is 2. And so by method 2, our residue at negative I is, again, it's the first derivative, the m minus first derivative over m minus 1 factorial, evaluated at that point. And so again, some computation, you get pi over 8, and this time it's minus I over 4. All right, so those are the residues in that case. You see the basic game is to, well, you identify your poles, and then you try to write your function as an analytic function divided by z minus pole to the m. All right. And I think maybe one more example to make sure we're okay with this. So the example will be to compute the residue of f at w, where f of z is z plus 1 divided by z squared plus 4 times z minus 1 cubed, and w is any pole. Of f. Okay, so again, you want to try to identify like where your poles. Poles are going to be places outside the domain. So what's outside the domain? Well, anything where this denominator is equal to 0 is going to be outside the domain. So let's make that clear by factoring. Z squared plus 4, that's z minus 2i times z plus 2i. And then we have that z minus 1 cubed. So it's clear that we should be focusing on the points 2i, negative 2i, and 1. Okay, and so let's see, so for 1, so we can write our function just as we did before. We have z plus 1. We can pull some of those denominators up, z minus 2i times z plus 2i. Divided by z minus 1 cubed. Right, and so we see clearly, so this shows that that 1 is a pole of order 3. Right, because you have the numerator is analytic near 3, right? It's it has a defined value at 3, and those are analytic functions. Just rational functions, and they also they don't vanish at 3, so you don't get the value 0, and so you have this non-vanishing analytic function in the numerator, and then divided by z minus 1 to the third. That's a pole of order 3. Alternatively, we have z plus 1 divided by z plus 2i times z minus 1 cubed. and then all that divided by z minus 2i. For similar reasons, this tells us that 2i is a pole of order 1. And then we have z plus I divided by z minus 2i times z minus 1 cubed over z plus 2i. And again, similar reasoning tells us that this is that negative 2i from this expression is a pole of order 1. Okay. And then, well, not only does this process tell us what our poles are and what order they have, but they're also instrumental to deducing what the residue is, right? Because for the pole 1, so for 1, so our pole 1, we just look at the form of our function up there. We have our k of z is equal to z plus 1 over z minus 2i times z plus 2i is, again, just from the original expression, that's z squared plus 4, right? And then we have our m is equal to 3. So what we have to do is compute the second derivative, right, m minus 1 derivative at our pole. And then that divided by 2 factorial, so just divided by 2. That's going to be equal to the residue of our function. Sorry, I should have put that first. Residue of f at 1. That's equal to that second derivative of k at 1 divided by 2. And after some computation, you have to, it takes some work because you have to take the second derivative of that rational function. But what it comes out to be, and you should check if you'd like, that it's negative 12 over 125. Okay, and then we just go down the list. For 2i, our k of z is z plus 1 over z plus 2i times z minus 1 cubed. And here we get a break because m is equal to 1. We have a pole of order 1, and so the residue of f at 2i, that's equal to the m minus first derivative of k. That's the 0th derivative of k. That's just the value of the function k. That's just k itself. And then evaluated at the pole, right, divided by 0 factorial, which is just 1. But just so you don't forget the factorial part there. And so we just have to plug 2i into k. And while that's relatively trivial, you do have these divisions by complex numbers, so you got to work them out. And if you do that, what you get is 24 minus 7i over 500. Okay. And then negative 2i, very similar. Our k of z in this case is z plus 1 over z minus 2i times z minus 1 cubed. Again, m is equal to 1, and the residue of our function at that pole is this k here, evaluated at negative 2i. So m is 1, so m minus 1 is 0, so that's the simplest case. And in this case, what we get is 24 plus 7i over 500. All right, so that is how you handle computing the residue in the case where we have a pole. All right, so we just saw some examples of how relatively simple it is to go about computing the residue of a function at a pole singularity. All right, and there's not really anything to do in the case of a removable singularity because your function is just analytic, and so the integral around a small circle going around your singular point is actually just 0, because you can extend your function across that singular point. But the only remaining case is when we have an essential singularity of our function. So how do we compute the residue in that case? Is there some special way to compute the residue that avoids the definition using the integral? Well, okay, so let's think about it. The key to our easy computations that we were just doing in the case of a pole was the Laurent series, right? That we had basically the fact that the residue is the -1 coefficient of the Laurent series of our function f. So the Laurent series for a pole only involves a finite number of negative powers of z minus z naught. But our experience with power series, we're used to dealing with sort of arbitrary powers of z minus z naught, arbitrary positive powers, right? Sums of arbitrarily many positive powers. Those make up the power series. So it's kind of natural to wonder whether you can go in the negative direction, right? So you take a sum of arbitrarily many negative powers of z minus z naught with coefficients, whether that kind of concept is a natural one to explore. And that's what's called Laurent series. And so it's basically natural to wonder, if you have a function, you have an essential singularity, is it possible that we can still maintain this Laurent series, but now we're going to entertain the possibility that there are infinitely many terms in the negative power direction. So we have the regular ordinary power series going in the positive power direction. We're allowing infinitely many terms there. If we allow infinitely many terms in the negative direction, perhaps we can allow perhaps we'll have such an expansion in the case of an essential singularity. And if that's the case, it might be plausible that we would still have that the residue of our function at our essential singularity is the -1 coefficient there. And so we could maintain some continuity with our previous methods, or generalize our previous method. And that all turns out to be the case. So what we're looking for here is essentially then just a generalization of Laurent series for a pole to a more general case where now we're going to allow infinitely many terms with negative powers of z minus z naught. Okay, so this is the result on Laurent series. So here's the setup. We suppose that f is analytic on a domain which contains an annulus. So you should refer yourself to this picture here. The domain is in green. The annulus is in A. The annulus is just a region between two disks the region between two circles. So the exterior of one disk and the interior of a larger disk. And just note that we allow the case that the inner disk has 0 radius. So it could be that it's just everything outside of a point and then inside some disk. So that would be like the case where you have an isolated singularity, right? Your function is analytic not at the center point, but then in the rest of some disk. And we'd also allow that the radius of that larger disk could be infinity. So you might want to think about the case like the non-zero complex numbers in this sense is an annulus where the inner radius is 0 and the outer radius is infinity. Okay. We're looking at a situation where our function is analytic on a domain that contains this annulus. All right. And z naught is a point that's not in our domain and is kind of at the center of this annulus. And it's the center of the little disk and the big disk that compose that annulus. And so on this annulus, what we will find is that our function can be written as the sum of two series. One of the series is in positive powers of z minus z naught, and the other one is in negative powers of z minus z naught. And so we can write that this way. So generally you write it like this. Right, so when n is positive, that's just you get the ordinary sort of power series stuff. When the n's are negative, then those z minus z naught to the n, those are in the denominator, right? So you have the sort of rational functions there, simple rational functions. Okay, and so that first part, that the regular power series, that converges when your z is close to z naught, at least as close as distance r, and your f2, the negative powers of z minus z naught, they converge when z is further away from z naught, so further than this distance r. Okay, so we in this annulus we can break down our function into two pieces, and those pieces, they're both going to converge in the annulus itself and give the value f of z when added together. All right, so that's called the Laurent series of our function in this situation. So we'll principally be applying this in the case where our function has an isolated singularity at the point z naught, and then our inner radius is 0, and then we'll have some outer radius. The inner radius is that little r, and the outer radius is that capital R. All right, and I've written down the proof ahead of time because there's a number of details, and I think it'll just go smoother if I've already had it written out, and it's going to take maybe a little time to go through, so I was worried about having enough time to go through it efficiently. So I'll just walk you through the proof. Okay, so we're going to be working in this annulus A, where our function is analytic. And so first thing to note is that this annulus, it's an open annulus, right? So those circles at radius big and little r are not actually contained in the annulus, and they might bump up. So like right here in the picture, right, and right here in the picture, they actually bump up against the boundary of the domain. So they might not be contained in the domain of the function itself. So the first thing in the proof is when we're looking at our annulus. So here's our annulus over here with the outer circle in yellow and the inner circle in yellow close to z naught there. We want to be doing things with circular curves going around z naught, but since those we can't use the yellow curves themselves because they might not be in the domain of the function. So we just have to move in just a little bit. So that's essentially the first line. So we're going to take our gamma 1 here is this blue curve where we've just moved in a little bit from the boundary of the annulus itself. And our gamma 2 is going to be, we're just going to move in just a little bit from the boundary there. Okay, so that's the first setup. So we're just taking some R1. So R1 is going to be the distance of this gamma 1 from Z naught, and big capital R1. And then lowercase r1 is going to be the distance of gamma 2 from Z naught. Okay, so those are the radii of those circles. And little r1 is just a little bit bigger than little r, and big R1 is just a little bit smaller than big R. Okay, and all right, so first of all, we fix Z, so the Z that we want to look at. And so the amount that we've come in, so we've brought our gamma 1 is in just a little bit, but that gamma 1, that has to encircle our Z naught. So it's going to be a distance, so our R1 is going to be a distance further out than the distance from Z to Z naught. And our little R1 is going to be closer, is going to be less than the distance from Z to Z naught. So everything is just setting up to look like this picture here. So basically we first fix Z naught, fix Z, you draw this circle, gamma 1 inside the annulus but containing Z, and then you draw this smaller circle, gamma 2, which is in the annulus but is not containing the point Z. So Z is on the exterior of that disk that gamma 2 contains. Okay, so that's the initial setup. Now, the proof proceeds very similar to the proof of the power series expansion. So it helps to remember that what we did in the proof of the power series expansion of f of z in the case where your f was analytic. So what we did in that case, so maybe I'll just go over here. So in that case, what we had, it was a sort of similar setup. So we had, in that case, we had a point z naught, and we had a disk around that where we wanted to do our power series expansion, right? So you take so you took a z in there, then you come in a little bit, so you drew a blue curve like this, say gamma 1, and we took what we did is we took a little curve here around z, and what we know is by the Cauchy integral formula is that and let's call that red curve also gamma. And so by the Cauchy integral formula, what we know is that the value of f at z is equal to the integral 1 over 2 pi I times the integral over gamma of f of zeta over zeta minus z d zeta. So that's the first thing, but the second thing is that we want to center things at z naught. So we can actually trade this integral over gamma for an integral over gamma 1 just by the weak homotopy principle, which is actually just using Green's theorem. You're just applying Green's theorem to the interior of gamma 1, but the exterior of gamma, that region that's in between those two curves. So you can now trade this for an integral around that curve gamma 1, which is centered at z naught. And then things go much better if you use that gamma 1 curve there. So that's what we did in the power series case. So we want to do something analogous here. So what we do is we take that gamma curve to be inside the annulus that's made by the blue curves, by the gamma 1 and gamma 2, and we write down the Cauchy integral formula in that gamma, right? Because our function is analytic in that green region there, because it's inside the annulus, which is the yellow annulus, which is where our function is analytic. So we can apply Cauchy's integral formula there, and so we're at this line here, and we see that f has that standard expression, right? Integral along gamma of f of zeta over zeta minus z. Well, we want to trade that for an integral that's sort of more centered around z naught. The only problem is it's not equal to the integral around the big circle, gamma 1, as it was before, because in the case before, our function was analytic in this entire disk in here. And so we could apply Green's theorem to the exterior of gamma and the interior of gamma 1. But we can't do that here because our function is not analytic in that whole region that's outside of gamma but inside gamma 1 because our point z naught, for example, is not in the domain. So we have to do something else, and that something else is going to be to use both of the curves, gamma 1 and gamma 2. And so what we'll do is we'll look at the green region omega, which has the boundary gamma 1, gamma 2, and gamma, right? And we'll apply Green's theorem to that, right? So that's going to be analog of the argument we made in the case with the power series. So what we'll do is we'll apply Green's theorem to that region omega, right? And so the boundary of omega, that is, so taking the correct orientations into account. So gamma 1 is oriented correctly, but gamma and gamma 2, they're supposed to be clockwise because they're sort of in the inside of that gamma. So we have to put negative signs there. But once we do that, we can change that into this area integral here. And because our function is analytic in omega, this integrand is equal to 0. And so we get 0, and then we just rearrange our, so you just take all these curves in here and you rearrange that equation. So we find that the integral along gamma, you pull that to the other side, that's equal to the integral along gamma 1 minus the integral along gamma 2. So what we find is that our f, having this expression in terms of gamma, we can write it in terms of gamma 1 and gamma 2, as you see in this equation here. Okay, so now we've kind of written our f as the sum of two things, which are both sort of centered around the point z0 at the center of the annulus there. Okay, and then the next bit is going to parallel what we saw or what we did in the power series case. And so what we did in the power series case is you look at the integrands here. So you look at the integrand here and the integrand here. And well, they're the same integrand, right? And we want to write this as a power series in z, right? And so you look at your z here, and this is kind of reminiscent of the geometric series formula. So it's reminiscent of like 1 over 1 minus z equals 1 plus z squared plus dot dot dot. So you kind of want to use something like that, but you have to do just a little bit of massaging to it first, because in order for this series over here to converge, you need the norm of your z. Yep. Sorry, I just made a bunch of penmanship mistakes. Yes, you need your norm of z to be less than 1 there. So the natural place you can get a less than 1 is that on your gamma 1, your variable zeta, the norm of zeta minus z0, right? So the distance from that circle to z0 is bigger than the distance from z to z0, right? Which is just apparent from the picture, and that's in our setup. And so if we look at the quotient of z minus z0 over zeta minus z0, the norm of that will be less than 1 on gamma 1. And so that will be the natural variable to use in the geometric series. And you do a similar thing on gamma 2. So on gamma 2, zeta minus z0 is less than z minus z0 in norm. And so the norm of zeta minus z0 over z minus z0 is going to be less than 1. And so that will be our natural variable to use in the geometric series. And so what you do to apply that is you insert a z0 into those denominators. You add and subtract a z0 in those denominators, and that's what you're seeing in this line here. And also I've taken the minus sign that was in the f of z, and I've distributed it into the denominator. So that's why you see a plus sign here, where there was a minus sign up there before. So you get z minus zeta on the bottom. So looking right here, you pull that minus in and you get z minus zeta, and then you insert your z naughts, and so that looks like that. You group them as you see there. And then the trick is to, in the first one, you want to get z minus z naught over zeta minus z naught, because that's what's going to be less than 1. So you have to pull out that denominator, zeta minus z naught. And so that's just an algebraic manipulation there. And you do an analogous thing on the other side, but in that case, you want zeta minus z naught over z minus z naught. So you have to pull out z minus z naught, and then you get the integrand you see in that line there. Okay, and then valid for in the regimes you see there, those inequalities which I've discussed, what you can do is write that 1 over 1 minus the relevant quantities as geometric series. So that's sort of the main. This is the main step. The main trick is to write these things as geometric series. So you just write each of them as the relevant geometric series. The 1 over 1 minus whatever, that whatever is the ratio. Okay, so you just substitute that series in, and then the next line is just I pull the 1 over 2 pi I in, and I pull the f of zeta over zeta minus z naught and the f of zeta over z minus z naught inside the sum, because those are just constants with respect to that summation. So you're just doing a little bit of cleaning up there. Okay, so that is sort of the first part of the computation in the proof, and sort of the main idea is try to use the geometric series on the integrands. So the next thing to do is to write this, right? So we're trying to get a power series, and so you sort of want the sum to be the sort of main thing on the outside. So you want to interchange the infinite summation and the integration by pulling those sigmas outside the integral. And that is something that has to be justified in general. And the justification is actually basically identical to the one that we did in the case of the power series before. But I'll run through the argument again, at least in one case. So basically what you want to do, so we'll look at the second summand, because that one's looks different than what we had before in the power series case. So if we can do that one, we'll be confident that we can do the other one. So the basic idea is that if you want to interchange your integral and infinite summation, well, sort of the reason you believe that's the case is because you can interchange integration and finite summation, right? And so you can actually use that, sort of turn that into a proof. So the integral of this infinite summation, so I'm looking at this calculation here now, the integral of this infinite summation, well, what you do is that infinite sum is the sum of the first finitely so many terms plus all of the other stuff, right? So you separate out into the first finitely so many terms, and then you pull the sum out of the integral in those finite terms, and then you leave the rest of the infinite terms on the inside of the integral. And so that's what you see here. So I've taken the sum of the first so many terms, and the so many here is a capital N. And then I've just sort of rearranged things. So I've grouped terms in a particular way, and then I just left the remainder of that infinite sum in the inside of that integral. And now what you notice is that if you take this formula and you let capital N go to infinity, then what you get is on the left-hand side you have the integral of your infinite sum, and on the right-hand side you have the infinite sum of your integral plus some other stuff, right? And so what you want is that other stuff to go to 0, because then you will have shown that the integral of this infinite sum is the infinite sum of that integral. So what we're going to do is show that the stuff in red goes to 0 as capital N goes to infinity. Okay, and so all you have to do that is to estimate the size of that integral in terms of capital N, and show that as capital N goes to infinity, that size, that upper bound on that size, is going to 0. All right, so that's what we do, and it's just the max length inequality, basically, and then just remembering some of our setup here. So if you take a look at the absolute value of that integral, it's less than or equal to the length of the integral, the length of the curve. And so our gamma 2, that had radius little r1, so it's 2 pi r times r1 there, that numerator there. And then, so that's the length, and then we have to do the max of our function on gamma 2. the absolute value of our function. And so the absolute value of our function, well, our function is all of this nasty stuff here, right? It's an infinite sum, but the absolute value of a sum, infinite or not, is less than or equal to the sum of the absolute values, just by the triangle inequality and continuity. So what we can do is just take this infinite sum of the absolute values, and so that's all I've done there. I took this z minus z naught, this extra power of 1, and I put that out front. So that's where you got this 1 over norm z minus z naught there. Okay, so we've just taken absolute values there, and this thing, this in the blue box, that number, norm zeta minus z naught over z minus z naught, that is, so we'll just call that number rho, and remember that is that is less than 1, right? Remember, so on the curve gamma 2, that zeta is on that curve, and that curve is closer to z naught than z was to z naught, so that ratio is less than 1. So then we just we cancel the 2 pi here with the 2 pi there. We pull out the norm of f of zeta, and then we have the sum of rho to the n, with the little n starting at capital N plus 1. So what you can do is you can pull out rho to the n plus 1, and since every term in that series is going to have rho to the n plus 1 as a factor, you pull that out, and then you're just summing the geometric series with ratio rho. So that's where you get this 1 over 1 minus rho there. That's just the sum of that geometric series. You got the max of your function along the curve, so along gamma 2, and the last thing is this yellow thing, the R1 over norm z minus z naught. Well, again, actually that's just rho again, and that's less than 1. So since that's less than 1, we can just, since we're using an inequality, we can just drop that. And so as n goes to infinity here, you just have this is just a fixed number, this is just a fixed number, and then rho to the n plus 1, well, that exponent's going to infinity and rho is less than 1. So that's going to 0 as capital N goes to infinity. So that tells you your red box goes to infinity. And so your red box goes to 0. And so what you see is that the integral of that infinite sum is the infinite sum of the integral, which is what we are trying to do. So we can interchange the integration and the summation. And what we find then is the result here. So after you pull out the sum, what you find is your f of z, right? So remember our computations were that f of z was equal to this sum here, right? So we had, f starting with f of z, you find that it's equal to the sum of these two integrals of infinite sums. After you pull the infinite sums out, you have the sum of two infinite summations of integrals, and then since your z minus z naught doesn't involve any zetas, you can pull them out of the integral. And so you just have the integrals, those integrals there, times z minus z naught to the n and z minus z naught to the negative n plus 1. So that's first and second term respectively there. So that's what we've come down to. We're almost to the end. The rest of this is just cosmetics, really. We've done all the hard stuff up to this point. So the first term there, that'll be our f sub 1 of z. So that's this is the sort of normal looking power series, positive powers of z minus z naught. And remember, this is valid when the norm of z minus z naught is less than or equal to the norm of zeta minus z naught, which was because that was what we needed for our geometric series to work out. Actually, I just realized that should be a strict inequality. Let me fix that. So this should be a strict inequality, and this should be a strict inequality as well. Yeah. Okay. And right. So that's valid in that range, and since R1 was arbitrary. So R1 was an arbitrary number we started with less than R. So this series is going to be convergent valid series for any. So this is going to work for any z which is within R of z naught. Okay, so the R1 we started with was just this perfectly arbitrary choice we made. Right, so that was the part where we came in from the outer part of the annulus at radius capital R. We came in just slightly, just a little bit, right? And the amount we came in by was kind of arbitrary. So that's going to work with for any R1, which is just slightly less than R, and so therefore it has to work whenever z is within distance of R of z naught. And for similar reasons, our f sub 2, that's going to be valid. So we've seen that this is valid when z is at least a distance of little r1 from z naught, and that r1 was arbitrary. So if we allow that r1 to relax back to r, we see that this must be valid for any z which is at least a distance little r from z naught. Okay, so just sort of noticing the validity of the domain of validity of these series expressions when they converge. And then what we do is in F2 up here, right, just to make things look more uniform between the two sides, what you can do is realize that this n here, if you set that n equal to a new variable, which is negative the quantity m plus 1, so now I'm looking down here, then you would have f of zeta over zeta minus z naught to the m plus 1, which looks a lot like the right-hand side over here. All right, so this is going to allow us to have some uniformity between the two expressions, f1 and f2. So setting n equal to negative m plus 1, we get this expression here, right? And you can easily invert this to see that m is got to be equal to negative n plus 1. So that tells us that this negative n plus 1 power of z minus z naught is a z minus z naught to the m, and that when n going from 0 to infinity, that's the same as m going from negative 1 to negative infinity. Right, so we can rewrite this as a sum from negative 1 to negative infinity, where the coefficients here, these integrals, the integrand has the same form as the integrand over here, and the powers of z minus z naught look more like the powers of z minus z naught there. So algebraically, formally, those expressions look a lot more similar. And so what we can do is just these integrals here, the 1 over 2 pi I times those integrals, those are going to be the coefficients of our series. Right? So we're just going to call those an for appropriate n. So we have positive powers here, n going from 0 to infinity. This one, our n going from negative 1 to negative infinity. And so we can write that as a sum here for negative infinity to infinity, a sub n times z minus z naught to the n. And a sub n is 1 over 2 pi I times the integral over the appropriate gamma curve of f of zeta over zeta minus z naught to the n plus 1 with respect to zeta. And that's, you use the curve at a larger radius, that's the I equals 1 curve when n is non-negative, and when n is negative, you use the curve that's closer in to z naught. That's the I equals 2 curve in our setup. And that completes the proof. So that shows that our f has a Laurent series. and it tells you what the coefficients of that Laurent series are. They're these integrals. And as a bonus of that, we note that indeed the -1 coefficient, right? So the coefficient of z minus z naught to the -1, well, that's going to be when n equals -1, right? So we just plug that into this this integral formula here, and we find that a sub -1 is 1 over 2 pi I times integral around gamma 2 of f of zeta d zeta. Well, that gamma 2 is just a circle of a small radius around z naught, right? And so this is exactly the definition of the residue of our function f at z naught. So we see that the residue of our function at our singular point is indeed the coefficient of 1 over z minus z naught in the Laurent series. And so in general, the residue is always going to be computed as the coefficient of 1 over z minus z naught in Laurent series. And so that gives us a method of computing the residue that we should try to find a Laurent series expansion for our function, and then we'll have an alternative way of computing the residue. And that will make our residue theorem a really powerful practical tool for computing complex line integrals that enclose singularities. And we'll see how we can use that to actually solve some calculus style definite integrals. And we'll do that shortly. So I think that's all we have time for right now. So then the next thing we'll do is we'll compute the residue using Laurent series of some other examples involving essential singularities, and then we'll talk about computing real integrals using the residue theorem.